Hi dear students, I'm Dr. Mashu. Welcome to my class. Today I would like to discuss pyrosequencing. Okay, pyrosequencing. Let's see pyrosequencing. Okay, let's see pyrosequencing. So we discussed about Sanger's method of DNA sequencing, automated DNA sequencing. But this pyrosequencing is differ from the Sanger's sequencing and the automated DNA sequencing. Okay, this pyrosequencing is differ from the automated DNA sequencing and Sanger's basic method of sequencing. And this pyrosequencing relies on the detection of pyrophosphate released and the generation of light on nucleotide incorporation. Okay, this in the case of Sanger's method of sequencing, we are using chain termination method by the use of dideoxynucleotides. Okay, but this pyrosequencing is relies on the detection of pyrophosphate release and the generation of light on nucleotide incorporation. Okay, nucleotide incorporation, and the name pyrosequence is due to its principle. Okay, the name pyrosequence is formed due to its principle, that means detection of pyrophosphate release. Okay, this method of sequencing is relies on the release of pyrophosphate. That's why this method is called as a pyrosequencing. Okay, and now you can see the principle of this. See here, when this is the DNA strand. Okay, this is the template DNA and this is the primer. When we add at the time of when DNA polymerase add a DNTP, okay, add a DNTP nucleotide into this strand primer to the primer. Okay, that primer that will add, that's DNA polymerase add a DNTP to this primer. That time this DNTP will be attached here, and that time one pyrophosphate is released. Okay, when add a DNTP, that time one pyrophosphate is removed. Okay, one pyrophosphate is released from this DNTP. Okay, and that when a nucleotide is added to here, that time from this DNTP, one pyrophosphate is released, and that pyrophosphate is reacted with ATP sulfurylase enzyme. Okay, ATP sulfurylase enzyme in the presence of adenosine 5 phosphosulfate. Okay, adenosine 5 phosphosulfate, that means APS. Okay, this PPI will be converted into this pyrophosphate will be converted into ATP in the presence of ATP sulfurylase enzyme and adenosine 5 phosphate. Okay, this ATP sulfurylase will convert this pyrophosphate into ATP. Okay, and this ATP will use as a substrate. ATP will involved in the reaction of conversion of luciferin into oxyluciferin. Okay, luciferin into oxyluciferin by the enzyme called luciferase. Okay, this enzyme luciferase will convert this luciferin into oxyluciferin by using ATP. And this that oxyluciferin, okay, that generate visible light. Okay, that generate visible light, and this light will be detected by our detector, and that depends on the light, that detector will give a pyrogram, and from that pyrogram we can easily detect, we easily will get the sequence of the DNA. Okay, now we can see what are the basic steps, basic procedure involved in the pyrosequencing. Okay, what are the basic procedure on the pyrosequencing? To do the pyrosequencing, we need DNTPs. Okay, we need all DNTPs like DCTP, DGTP, DTTP, and DATP alpha S. Okay, DATP alpha S. Why we are using DATP alpha S is the modified form of adenosine triphosphate, and why we are using DATP alpha S here is because when here you see that pyrophosphate is converted into ATP here. Okay, this pyrophosphate will be converted as told in the principle of this procedure. This ATP is the when we are using this in the DNTP, this we are using the normal DATP. So the luciferase will use this ATP also uh, for the production of oxyluciferin and light. So that why we are using D alpha ATP, DATP alpha S here, and we have to use DNA polymerase ATP sulfurylase enzyme adenosine 5 phosphosulfate luciferase luciferin apparase. Okay, apparase. Okay, that means for the reaction we need DNTPs. In that case, we use DCTP, DGTP, DTTP, and DATP alpha S. Why? Because we are using DATP alpha S here. Means here you see the luciferase enzyme. That luciferase enzyme have a substrate ATP. If you are using the normal ATP here, that time this luciferase will be use this our ATP for production of oxyluciferin and light. So that for here ATP there will be synthesized from this PPI. If you are using normal ATP here, that luciferase will take this ATP for the synthesis of light. So to avoid that noise, we use DATP alpha. Yes, there's a modified adenosine triphosphate. Okay, that will be used for the synthesis of DNA and DNA polymerase and ATP sulfurylase and adenosine 5 phosphosulfate luciferase luciferin apparase enzyme will use. Okay, and this sequencing also depends on the synthesis of complementary strand DNA by enzyme. Okay, this sequencing also is depends the synthesis of complementary strand DNA by enzyme. Okay, when in all sequencing method in the Sanger's method of sequencing, we'll add all DNTPs. Okay, all will add all DNTPs in all time into the reaction. Okay, that means in every time all DNTPs will be present in the reaction mixer. But in the case of pyrosequencing, a single type of DNTP only will be added to the reaction mixer at a time. Okay, that means at a time only one type of DNTP will be present in the reaction mixer. Okay, for example, here you see the time here we will add only one DNTP. So for example, we are adding DGTP. Okay, we are adding DGTP. That time the reaction mixer only contain DGTP. Okay, DGTP. That time only we contain DGTP. And if that DGTP is suitable for this strand, okay, for the synthesis of this nucleotide, if it is complementary, G is complementary, that if that G will be bind here. If that DNTP is not suitable, okay, that a single type of DNTP is added for the synthesis of DNA strand at a time, and if that DNTP is not suitable, then that nucleotide will be degraded by apparase enzyme. Okay, that unincorporated. Okay, unincorporated. If that sequence nucleotide is not suitable for here, it is not complementary to this, then that sequence will not be incorporated here. That unincorporated nucleotide will be degraded by enzyme apparase enzyme, and the reaction can restart with another nucleotide. Okay, that means we add DGTP here, so that DGTP is not suitable, then that apparase will remove that DNTP, that DGTP from there, and it will add another one next nucleotide, that may be DCTP. Okay, DCTP will be add here. So that time this DCTP is complement it here, that time that will be add. Okay, that will be add. So when it will be incorporated here, that time that will produce a pyrophosphate. Okay, pyrophosphate, and that pyrophosphate will be converted into ATP, and that will be converted into oxyluciferin, and that ATP used to convert luciferin into oxyluciferin and produce light, and that light will be detected by the our detector, and from that we'll get the sequence. Okay, that's the procedure. Okay, uh, when we at a time only one type of nucleotide will be present in the reaction mixture. If that nucleotide is not complementary to the that our template nucleotide, then that nucleotide will be degraded by the enzyme called apparase, and the reaction restart with the next nucleotide. Okay, another nucleotide. Sometimes DGDP is added, that DGDP is not that's suitable, so it's that unincorporated nucleotide will be degraded by apparase, and the system will restart with another. Sometimes this be DCTP. So if DCTP or next nucleotide is suitable, then that time DNA polymerase will be added to here, and that time inorganic pyrophosphate will be released, and from that ATP sulfurylase convert the TPI to ATP in the presence of APS, like we explained in the uh, principal part in the previous slide, and produce light. From that light we'll get a pyrogram. From that we can easily get the sequence. Okay, detected by the camera attached on a detector, and that will be analyzed. Okay, the light produced by luciferase catalyzed reaction will be detected by the camera attached into the detector, and that will be analyzed. And the amount of light produced, okay, the amount of light produced at a time is proportional to the amount of ATP produced. Okay, the amount of light produced at a time is proportional to the amount of ATP produced. Okay, so here you see, okay, for example, here you see these are the template DNA. Okay, these are template DNA. Okay, here this is the our template DNA. Okay, these are template DNA. These are the primer. This is the primer. So the system will add, for example, the system add D alpha D-ATP alpha S. Okay, D-ATP alpha S to this reaction. Okay, D-ATP alpha to this reaction for the amplification. The time DNA polymerase will come here, and it will check whether this will be suitable here. You see, this is a here is a. So it will be complementary to this one will be a T. Okay, it will be T. But here this D-ATP alpha. Okay, this is a D-ATP alpha. So that it is not complementary. That's why that's enzyme called apparase will be degrade this D-ATP alpha S. So here there will be no light, because here it will come with a T. Now see, and after that, that total DATP will be degraded by the apparase enzyme. Then the system will restart with add another second nucleotide. That's be DCTP. Okay, DCTP will be add, and that time DNA polymerase will check what is suitable here. So here A is the, so C is not suitable here. So here also the DCTP will be removed by the apparase enzyme, so there will be no light. Okay, no light, and then system will check another, then will add. Okay, that system will add DGTP. Okay, DGTP will be added here. So here also G is not suitable here, so that also that DGTP will also be degraded by the apparase, and so there will be no signal here, light will be here, and the system will next add DTTP. DTTP system will the add, then DNA polymerase will check this suitably here. So here the A is there. A means adenine is there, so it's complementary. T is there. T is there. So T is there. So the T will be added here. So at that time pyrophosphate will be removed, released, so that pyrophosphate will be converted into ATP, and that ATP will be used for the conversion of luciferin into oxyluciferin, so light will be produced. So here you see one signal is there. So one signal, there's one here you see one signal, that means that in this cycle one sequence plus this one signal is there, so we can say here the sequence is the T. And then again we'll start. So up to this it is synthesized, and then again it will start, and here you see again it is started. Okay, again start with D alpha T. Okay, D ATP alpha is added here. You see here D ATP. That time D ATP alpha is added here. So D ATP alpha is added here. That time you see here T is there. So here A also will be there. A how to come here. So that time one signal will be here, and that same time also DATP will be present there, so we'll give two signal. Okay, that will give two signal because here 2A will be 1A and 1A will be added in a same addition of this DATP. So we'll get two signal here. So that means that we discussed is the amount of light produced at the time is proportional to the amount of ATP produced. Okay, so that means here 2T is there, so its complement will be A. It complementary will be A. So when we add DATP that time, 2 ATP A is be added here, so that produce 2 ATP. Okay, that will be add 2 ATP. So that means when here is a T is there, 2T is there, when we add DATP alpha is, so that time this complementary this T and this T1, this D alpha ATP will be added. That time 2 pyrophosphate will be released. Okay, 2 pyrophosphate will be released, and that pyrophosphate will be converted into ATP. So that ATP, 2 ATP will be formed, then that 2 ATP will be convert luciferin into oxyluciferin. So that time we'll get two light signal. So here we mark a two light signal. That means nearby there is a two A sequence is there. Nearby A sequence is there. That's why it's got two signal here. And again the system will add DCTP. Okay, again system will try to add DCTP, but up to this amplification is over. Now this part we have to add. Okay, now we have to add to this sequence. Then system will check whether C is suitable to here. That time system will found C is C is not suitable to here. So that C will be degraded by Pyrosequencing enzyme. Okay, that's DCTP will be degraded by the Pyrosequencing enzyme. So there will be no signal. Okay, there will be no signal. And again system will add DGTP. Okay, DGTP. So here see three C sequences there, and its complement will be G. Okay, then they will be complement will be G, and so three DGTP will be added here. 1, 2, 3. So 3 DGTP will be added here, and that 3 DGTP will be produce 3 pyrophosphate, and 3 pyrophosphate will be converted into ATP, and that ATP will produce convert the luciferin into luciferin into oxyluciferin. So we'll get 3 light signal. Okay, so we will get the in this when you add DGTP, we'll get a 3 light signal. That means here we can see the 3 light signal means there is a 3G is produced. Okay, 3G is there, so that's why it's given that 3 signal. Okay, and next up to here we have synthesized, and we'll add DTTP. Okay, this will repeat as like a cycle. Here you see DTTP we added. Okay, DTTP we added. That time this system will check whether is DTP is complementary here. So you check here, is there. So T is complementary here. So you see when added to T, that time they will produce a light signal, and here you can see one signal is there. Okay, one signal. So we can read from here. We can read the sequence. First, we'll get a T A and G and T. This is our sequence. You see T, A, A, G, G, T. This is the sequence. Okay, this is the pyro sequence. Okay, this is the pyro sequence. So I hope you understood this. Thank you. Thank you for listening.